Here, the schedule of classes, and we're still in chapter 16 here. Waves, the sound, wave interference. Wave interference. So we're almost coming to the end of the semester. Our last, final exam is going to be next Wednesday, Wednesday of next week. We still have this other meeting here, and which we are going to do the lab number 7, moment of inertia. And let's not forget, report for lab 7 is due, no, wait a minute, lab 6. Report for lab 6 is due Wednesday. Okay, report for lab 5 was due last Wednesday. Right, and here you go, report for the lab 6 is due the day after tomorrow. And let's continue on waves. I found here some nice slides that I have lost there somewhere in my computer. Okay, so when you think about the waves, think about attaching, for instance. Let me put here. Think about attaching a string to the end of this oscillator here. It oscillates back and forth and generate what we call a train of waves or a periodic wave. That's a very important type of wave, periodic wave. Okay, but so first let's go talk about waves in general, and then we zoom in on periodic waves. That's what we usually do in this course. Remind you that there is a very generic type of wave. There are many types of waves, but the most important one are periodic waves. Okay? Periodic waves are waves that keep on repeating themselves. And among these periodic waves, there is an even more important type of wave that we call planar waves, which mathematically speaking, are expressed in terms of sines and cosines. So so planar waves is the one that you must be focused on. So planar waves are the ones that you must focus on. Why is that? There's a reason for that. The reason is because any type of periodic wave can be expressed in terms of sines and cosines. That's the reason, okay? That's the reason. So when I mentioned to you before that a one-dimensional wave can be expressed in terms of a function like that, okay? Remember that? As a function of position, a function of time. When we are talking about periodic waves, okay, and I'm going to put a P here for periodic, PER, okay? The functional dependence of a periodic wave, of any periodic wave, It doesn't have to be sines and cosines. It can also be, square waves, can be triangular waves, and so on. Okay. The functional dependence of any periodic wave can be written down in terms of a summation, okay, and infinity of sines and cosines, sines and cosines. That's why those planar waves are so important. Of course, we must have a coefficient here that goes in front of it. Okay, and then I'm gonna break the spoiler alert here, right? Eventually, and the waves can be written down in terms of something like that. And I'm going to elaborate a little bit more on what goes here inside this part of the wave, okay? But don't forget, we are going to concentrate on this type of waves here. And by the way, to be even more genetic, we can put a case of I there as well. To be even more genetic. Okay? And now let me give you some qualitative, here is some quantitative type of explanations for the wave, okay? But let me give you some qualitative illustrations of waves. Like I said, if you have a string, infinitely long string, semi-infinite long string, okay? Because this end here is fixed, and then the other end is so long that we cannot see it, right? We can say that infinitely long. If you have a string, an undisturbed string, the string looks just like that. I am neglecting the mass of the string. So there is no sagging of the string itself. However, if you disturb a string, one way of producing a wave is by disturbing a string. What you see right in here is a special type of wave that we call a pulse, okay? That is produced just by raising the string and lower it just once. There is no vibration whatsoever in there. But either way, this pulse that you see here can still also be expressed in terms of sines and cosines, the summation of sines and cosines, okay? So a pulse looks just like that. You have this bump, right, propagating along the string. That's and the waves, they are subjected to reflection as well. In the case of the pulse, if you have a fixed end right here, the string now is not an infinitely long string, right? Now is a finite string. We have one end here and another end here. This end here is not fixed, okay? It's movable, but this one here is fixed. So once you have a string like that, a wave like that, when the wave reaches the end of the string, it's going to reflect, and it's going to reflect upside down, okay? That's a very important characteristic of a wave. It gets reflected upside down and moves in the other direction, the negative direction, okay? That's a qualitative way of looking at a wave. It's, even though it's qualitative, it's still important. We can prove that mathematically. Oh, I did something here. Let's see. What? Ah, I know the problem. I know what the problem is. Yeah. Here you go. Now, nope. Students coming. Here you go. Come to the back. Okay. We're going to do the same to this one, so it looks nice, right? Another one. Here's the wave propagating backwards. Okay. So let's document that. Okay. There are many types of waves, but the most important ones are periodic waves. Ones are periodic waves. Periodic waves are waves that keep on repeating themselves. It can be the sine waves, can be the cosine waves, can be even the square waves, can be the triangular waves, and so on. And among these periodic waves, there is an even more important type of wave that we call planar waves, which mathematically speaking are expressed in terms of sines and cosines. So planar waves are the one that you must focus on. Why is that? Because any type of periodic wave can be expressed in terms of sines and cosines. Here is, any type of periodic wave. Okay? So how waves behave? The waves can propagate along the positive direction. And mathematically speaking, waves that propagate along the positive direction are expressed with this negative sign. You have to memorize that, okay? Negative sign means positive propagation of the wave. And along the negative direction. Notice that I'm writing down as a f function, as a generic f function. Okay? For a planar wave propagating along the positive and negative directions, planar wave that propagate along a positive, planar wave that propagate along the positive negative direction can be expressed mathematically as, good. So now you already know, right? I'm going to put it here, positive. I'm going to do even better. I'm going to put it like that. Everything. Okay, it can be a superposition of sines and cosines. And we do not have a sub I anymore, because I'm talking about what we call a monochromatic type of wave. And then the negative wave will be expressed with the sign here in the okay here, yeah, negative plus positive propagation with a negative, okay, right in here. And it's possible to prove that mathematically. It's it's possible to prove that mathematically. It's not difficult, but I'm gonna, I want to move forward. As I mentioned before, right? I'm gonna just repeat what I did last time, what I wrote last time, because this is important. Mentioned before, you go, a wave is closely related to oscillations. Oh. Ay. I'll have to force the thing. No, this is not what I want. For set numbering values. Good. Yep. Okay, an oscillation generates a periodic wave. The amplitude of an oscillation generates a wave with the same amplitude, and that is the amplitude that we have. The frequency and period of an oscillation generates a wave with the same period and frequency. That's what waves have that an oscillation has. And then there are other things that a wave has that an oscillation doesn't have. It has a speed. A wave has a speed. Okay, even better, a periodic wave. I'm going to put it here. It has a wavelength. Let's put it here first. We need the wavelengths. Okay. Our wavelength before speed. We need the wavelengths before we can define the speed. That's why I changed the order. A wave has a speed. A wave has crests, valleys, and nodes. Okay. And there is a relationship between the speed, wavelengths, and period. Okay. Okay. So let me get another one here. I want to remind you of what a wavelength is, right? Illustrations for simulations right here. Right here. Okay. What is the wavelengths? Wavelengths is the distance from crest to crest. The shortest distance from crest to crest. Okay. And I'm going to put that here. The shortest distance from crest to crest. That's what wavelength is. What is the relationship between the speed? What's the relationship for this? What's the relation for the speed of a wave? That I'm gonna write down as being v. Let's not forget, right? V is it's not difficult to memorize this relationship for the speed of the wave. Okay, just remember, just be reminded that v in general is delta x over delta t, right? The question is, what's going to be the delta x of the wave to express that in terms of speed? Okay, the delta x for the wave in this case is going to be the wavelength because it's a distance, right? And the delta t is going to be the period of the wave. We here write that as being, we express that differently, lambda divided by period t. So if you have the wavelengths and the period of the wave, you can find out its speed. But let's not forget that the period is just the inverse of the frequency. So that's another way of writing down the speed of the wave. This is the most generic expression for the speed of a periodic wave.
Professor, I have a question.
Yeah, go ahead.
Is this going to be on the final exam?
Yeah, everything is in the final exam. Everything is gonna be the.
Oh, okay. I was just wondering because like I'm looking at the 2022 note, and chapter 11 to 17 are excluded. That's why I was wondering.
Chapter 11. We skipped chapter. Are you talking about chapter 11?
To 17.
Let me see. Well, stick to the note of 2023, okay?
Oh, okay.
Okay. Last year, everything. Let me see here. You're telling me that just chapter 11 to 17 on the final. That's what you said.
Yeah, sections for the final exam. It's like
No,
I don't know if I read it right.
Yeah, there's something wrong there. All my final exams are everything. Okay, there might be something wrong in there.
Oh, okay.
But I can check later on. You show me where you saw that, okay, and then I'll try to figure out. But you know that. Let me just final exam is everything. Okay, everything. Okay, and I even have no. I'm not gonna look into the. Let's just you know, hang out after the class and then show me where you saw that. Okay. Okay. So.
Okay. Thank you.
Okay. Now let's go back here to the notes. Final exam is everything. Let's not forget that. Now, what else we have to know now? Okay. Waves can reflect and refract. Okay. Reflections. And refractions. Let's see, reflections. You can reflect. You can have a reflection of a wave out of a fixed and loose end, out of a fixed or loose ends, right? And I illustrate some of that for you here. Here you go, going back here. Okay, here you go. The pulse is easier. It's easier to illustrate that with a pulse. I'm not illustrating that with a train of waves because it's easier to visualize that with a pulse. Okay, so here you go. The pulse gets to the fixed end and it reflects back. When it reflects back, upside down. I'm not going to prove that mathematically. It's possible to prove that mathematically, but I'm not going to do that. Okay. So just remember that for the exam or any other problem that you do it. Okay. So whereas the wave was initially propagating to the right, x minus vt, right, in the argument. Here you go. That's x minus vt in the argument. Once it reflects, it's going to propagate to the left, which is going to be x plus vt in the argument. And there is something funny here. Let's see here. Send to the back. Okay, now looks better. Looks better. Here you go. Propagating to the left. Backward, forward propagation here. Okay, forward propagation here. Backward propagation here. But then that was the reflection out of a free end. Of a fixed end. What if we have a free end instead? Free end instead, the situation is different. Once the wave gets to the end, see, I put here a little loop here to show that the wave has the string has a loose end. This loose end during the reflection, this loose end is going to move up and down, okay? And then when the wave reflects, it's going to reflect upwards, okay? In a mathematical sense, okay? Reflection Original wave, let's put it this way. Original wave is going to be expressed as, here you go, x minus vt. See that? And I'm going to specifically state that's going to be the forwards. And I'm going to put an amplitude here too. Right? Original wave. Amplitude is not a function of x. Amplitude is a constant. It's not a function of x. It's not a function of t. Okay, original wave. Reflection out of a fixed end. What happens to this wave when it reflects out of a fixed end? You know, the amplitude change goes downwards. That's why we have a negative sign. And this sign changes as well. And the wave becomes a backward propagating wave. Okay? And then we can do reflection out of a loose end. Out of a loose end. What happens when you reflect out of the loose end? You know, I'm gonna emphasize that we have a positive here, okay? The amplitude doesn't change. Consequently, the backward propagating wave becomes positive. That's reflection. Now we can talk about refraction as well. What's refraction? Refraction of a wave. Okay, I'm going to give you an example of refraction of a wave. Okay, free end. Here you go. Reflection or refraction or transmission. Okay, transmission is a better word. Refraction or transmission of a wave. And then we start with the original wave. Okay, I'm gonna copy and paste everything here. Original wave start like that in a forward propagating direction. And then we have transmissions of wave from a lighter to a heavier string, okay? From a less resistance to a more resistance medium. And here I illustrated the less resistance medium, the lighter medium, with a thinner string, okay? And the heavier string, the more resistance medium, is a thicker one. So this wave is propagating right in here. It's gonna reach this interface between the lighter and the heavier string, and something is gonna happen at this interface. Some of the wave is going to be transmitted, and some of the wave is going to be reflected. Okay? That's what's gonna happen. Here you go. Reaches here this point because it is a heavier medium than the other. The heavier medium behaves as though it is a fixed end. Okay? And this wave is going to split into two parts. A little bit more complicated than reflection, right? At the loose end, fixed ends. Some of it is going to transmit forward, and some of it is going to transmit backwards. Okay? And I'm going to put one more. Yeah, one more. And this one too is going to move a little bit forward, right? So you have the illusion of a movie being played. Here you go. So here you go. Notice that the amplitude changes during the reflection and refraction, okay? And depending on the medium, you're going to have different amplitudes, okay? So here you go. We can elaborate that here as well. Original wave, let's say refraction or transmission wave. Original wave, that's the original wave. Let's see, lighter to heavier string, okay? The resulting wave, and now the resulting wave I'm going to write down in terms of it's going to be a wave in the forward direction plus a wave in the backward direction. The wave in the forward direction is going to have amplitude in the proper, in the original direction, okay? But this amplitude is going to be less than that because the wave has to share, the forward wave and the backward wave has to share its amplitude, okay? There is conservation of energy, and energy is dictated by the amplitude of the wave, by the way. Lighter to heavier, and then we're going to have this term right here with the inverted amplitude and backward propagation direction, okay? Lighter to heavier string. And now that you know how it behaves like lighter to heavier string, you can figure out how it's going to be from heavier to lighter string, right? We're still going to have a forward and a backward propagating wave, and that's illustrated right in here. Heavier to lighter string. When I mean heavier to lighter string, I mean heavier to lighter medium, okay? Media. Here you go, approaching, it's gonna have a different velocity too, by the way. I should put that here. Here is going to be the original velocity, because it's reflecting back. No, here's gonna be the original velocity, and here's gonna be a different velocity because it's a different medium. Here too. See that? Now, if you look at right in here, this medium here, because it's heavier than the other, is gonna not only is gonna have a different velocity, but it's gonna have a smaller velocity as well. Heavier means more resistance to motion. That's why I put V1 less than V. Here is V, here is V1. Okay, forward, here you go, is going to be prime. And here is preserved. The velocity is preserved. The original velocity is preserved. I'm going to emphasize that here. Okay, heavier, lighter to heavier string. V prime, oh no, 1, 2, 3, V prime less than V. Okay. And because it's heavier to lighter string, now V prime is going to be greater than V. Make sense? Heavier medium. Heavier medium. Oh, give more resistance to motion. And heavier to lighter. Yeah, we did it. Do I have it right here? Forward propagation, yes. The velocity changes because it goes from one medium to another. The reflection, to a lighter, okay, to a lighter string, the amplitude doesn't invert. And I'm gonna put that here backward as well. Backwards. What else do I have to say? AF and AF less than A. I'm gonna center AF less than A, AB less than A. We have to have conservation of energy. Okay? I cannot say anything about AF or AB unless I know the details of the media, of the two media. And the same thing here as well. That's how we mathematically express what you see right here in those illustrations. Okay, let's play it again. Rewinding my movie, right? That's unbound medium. Okay, that's a finite medium. Okay, fixed end, loose end. Okay, and then we have refraction as well. Refraction or transmission. Refraction is the same as transmission. Okay. And then the other, you go. Oops, I gotta put one more. Move here to the left a little bit. Shrink it. And then shrink it as well. Ooh, like that. Okay. Well, whatever we are displaying right here also applies, like I said before, to a train of waves, to a periodic wave. Okay. And we're going to use that soon. Periodic waves. And okay. I'm going to be more explicit what this, for a planar wave, as stated before, for a planar wave propagating in a forward and backward direction, we have the following. I'm going to keep on repeating that. And so you can absorb it. Okay, here you go. But then I'm going to do something else I didn't do before. I'm going to eliminate this cosine term here. So it becomes simpler, okay? Forward will be the positive direction. Backward will be the negative direction. What I didn't tell you, this you should know, right? Remember that, don't forget that. X minus Vt forward, X plus Vt backwards. But then I put another term here. There's a reason why I wrote down that other term. Okay, the K parameter is there to ensure that the term in the argument of the sign is unitless. Okay, you cannot write, it would be incorrect to write something like that. Okay, the argument of the sign cannot have any dimension whatsoever because you cannot take the sign of the meter. Okay, that's why we introduced this other term here, the K term. But then you have to know what this K is all about. You have to know what this case is all about. And I'm going to tell you what this case is all about. Since this part here of the argument is in meter, the K must be in meter, inverse of the meter. Okay? Okay. The argument of any function, okay, I'm going to put it in capital, must be dimensionless. Okay? It would be incorrect to take the sine or cosine of a quantity that has a unit in meters, for instance. Okay? It's okay to take the sine or cosine of a quantity in radians or degrees, right? But that's because in both cases, these units are unitless, right? Are unitless. So to ensure that your argument, that the argument, right? That the argument of these functions are unitless, we must multiply x plus and minus vt by another parameter that cancels out the meter. Okay? So just by doing this dimensional analysis, we discover that K, the unit of K, must be in meters to the minus 1. Okay? Now the question is, what would that be? What would that be the relation? Okay? Well, the K is in reality, we can prove that as well. Okay? It happens that the K is given by, okay, K is usually called the wave number, and it's given by K equal to 2 pi over lambda. Okay? That's what K is. Oh, another one. That's what K, oh gosh. Get into trouble here is I want to put it. Okay, now we can do it. And now you can see that the wavelength is in meter, and this meter here downstairs is going to cancel with this other meter upstairs. Okay? That's how a wave is written down. Forward propagating wave, backward propagating, a planar, right? A planar wave is written down. Okay, there are different ways of expressing that. Let's not forget, right? All what we have here can be written down in terms of 2 pi over lambda. 2 pi over lambda. But then we can also expand this term here, and here writing it in a different way. Not just expand, but doing something else. Okay, here you go. We can here write our speed, different ways of writing the same thing, as being lambda f. Okay? Make sense? And then I can go ahead, oops, well, copy and paste here as well. But of course, I gotta change this sign, right? Change the sign here. Change the sign here. And then this lambda is gonna cancel out with this lambda. Okay? This lambda cancel out with this lambda. We are left with 2 pi f 2 pi f. And another way of writing the same formula would be, to go back to our k right in here. You're going to see that in books, by the way. You see this notation in books. And here writing this term as being the angular frequency, something that we have seen before. Okay? That one that we wrote down as omega. That's another way of writing the same equation, both for the forward and the backwards. Which one do I prefer? Notice it. Which one do I prefer? So you have those two options, right? Either write in terms of kx plus and minus omega t, or you write down in terms of k multiplied by x minus vt. Which one do I prefer? My personal, preference is this one here. That's my personal preference. Because it's easier to see that we have meter here and we have something 1 divided by meter here. Okay? In this equation here, we have to memorize only this parameter here, because the other three that are here are already very familiar to you all, right? Whereas in this equation here, you have to memorize not just this parameter, but this other one right here, okay? Examples of waves, right? Planar waves. Okay, on one. Find the wavelengths and speed of the following waves. Find the wavelengths, the speed, and direction of propagation of the following waves. There you go. This one here, I'm going to put down like, something very simple, and then we can go for something more complicated. 3 meters. Oops, the meter goes downstairs. Okay, and then find wavelength, speed, frequency, right? Frequency, period, and direction of propagation of the following waves. Pi. And now I'm going to put here, 3 hertz. That's going to be easy, right? If you see something like that in the exam, oh, this one. That's going to be, this one is kind of easy. That's already broken down for you, right? Okay. So, wavelengths. In the above, not everything is going to be easy. Some of it is going to be easy. The wavelengths. Lambda is going to be 3 meters. That's straightforward for both of them. 3 meters here, right? 3 meters here. Speed. Okay, speed. Well, we're going to find that out. Not yet. Not yet. Before finding the speed, we have to find something else. Frequency. Okay, frequency. Okay, frequency is obvious here, right? That's the frequency, 2 pi f, right? 3 hertz. Don't forget that hertz is 1 divided by second. Consequently, the second here in the t cancels out with the second downstairs in the hertz. And now that we found the frequency, we can find out what is the speed of the wave, right? The speed of the wave is what? Lambda divided by the period. But let's not forget that the period is the inverse of the frequency. And we end up with 3 meters times 3 hertz, which ends up being 9 meter hertz. And let's not forget that hertz is 1 divided by second, right? And we finally have, for this specific wave, let's see what's going on here. For this specific wave, we have 9 meters per second, like that. Sometimes we cannot calculate one of those parameters without finding the other one, right? That's what I did. First, I found the lambda, then I found the frequency, and from those two parameters, I find the speed. Okay, period. Okay, period is easy, right? Period is just the inverse of the frequency. One divided by 3 hertz, which ends up being 0.333, right? Seconds. That's the period of the wave. I'm gonna ask you something else too. Okay, I'm gonna put, 4 meter here. I'm gonna put 4 meter here, right? Find the wavelength, speed, amplitude, frequency, period, and direction of propagation. We need the amplitude too. I'm gonna put at the end, period, amplitude, and direction of propagation. The amplitude, is gonna be 4 meters, right? I put 4 in there. Direction of propagation, First wave is forward direction. Second wave is backward direction. Okay. And then you can have things more complicated than that. Okay, what if I, right? Repeat above, right? Repeat above example for the following waves. Go. Instead of 2 pi over 3 meters, I put 1 here. Instead of 2 pi here, I just put 3 hertz. Let's see what I did here. Oops. Okay, here you go. Same. Now it becomes a little bit more complicated. What do you do here? Just remember that this term here is going to be K, right? And just remember that this term here is going to be what? The angular frequency, omega. Okay? And omega is nothing but 2 pi f. 2 pi f. K is nothing but 2 pi over lambda, right? And then you solve it. That's some examples that you have. This is already 16.4, okay? What time is that? 9:46. Let's talk about the speed of a wave in a string. speed of a wave on a string. Okay? You already know that the genetic equation for any type of any planar wave, let's see, any planar wave propagating in any medium, right? The genetic equation of the speed of any planar wave propagating in any medium is given by, I wrote that down right in here. You already know that. The above equation applies to waves in a string, on a string, right? On a string, water waves, sound waves, even electromagnetic waves, etc. That's why it's genetic, right? And I'm going to emphasize the genetic. Okay. What if you want a particular expression of this speed for a wave in a string, for instance? An expression that does not involve the wavelengths of frequency, but the intrinsic parameters of the medium, okay? Intrinsic, and I'm going to emphasize here, intrinsic parameters of the medium. Okay? For this situation, for this case, we will have different expressions for different types of medium. Okay? The one that we introduce to you is the expression of the speed of a wave on a string of linear mass density. I want to put it mu, okay, and tension T. Oh, tension F. Let's put tension F. Here I'm gonna, okay. What you have to know, okay, keep in mind, what you must know. We can also derive that, but it's too much trouble to do that. And the book doesn't derive that for you either. It just gives you the expression. What you must know is that the speed of a wave in a string depends on the linear mass density of the string. Remember what you saw before? Here you go. Here's the string, right? This string here is heavier than this one. What does it mean it's heavier? It means that I have a higher linear mass density than this string here. Okay? The mass of this string divided by its length is greater than the mass of this string divided by its length. That's what we call linear mass density. Okay? Linear mass density mu is m divided by L. So if you get two strings of different linear mass density and same tension, we are going to have only speed. we were going to have different speeds. If you get the same string under different tensions, right, you're going to have another speed. And that's what I mean when let me give you an example here. I have one right in here. Okay, here you go. We do that in an experiment, in a physics experiment. Right in here. No, yeah. I got the wrong one. Okay, I got the wrong one here. Let's go back there. Okay, right in here. That's the one I want. So here you go. Here we have a string, okay? A string passing through a pulley with a weight stretching, a tension being applied to the string, okay? And then in the next drawing, I have the same string, but with a different tension. I added a second weight in there, okay? Even though those two strings are the same, have the same linear mass density, this string here is subject to a larger tension than this one. Consequently, the speed of this string, the speed of the wave of this string is going to be different from this one. Okay? And the same happens for this other case here. Same string, but with a third different tension. One tension, another tension higher than the previous one, another tension higher than the previous one. In all those three cases, you have different speeds of the wave. And what is going to be the equation? Okay, you have to know by heart. That depends on the linear mass density of the string and the tension of the string. And what's going to be the expression for the speed for this particular case is going to be square root of the tension. Okay, the larger the tension, the higher the speed. Can you remember that? That's not difficult, right? But don't forget, it's going to be a square root here, divided by the linear mass density of the string. The higher the force, the higher the speed. The heavier the string, the heavier the string, the lower the speed. Can you remember that? That's not difficult, right? If you are heavier, you have more inertia. Consequently, the speed is going to be lower. If you have more force applied to the string, then the speed is going to be higher. But don't forget, this is the tension. In your book, the linear mass density is written like that. Okay? 955. And then you have we have some practical applications of that. It's just like the guitar player, okay? The guitar player. You get a guitar, you apply more tension on the strings of your guitar, the speed of the wave is going to be higher. Okay? The speed of the wave is going to be higher. If the wavelength of the wave doesn't change, what does it mean? It means that the frequency of the string is going to be higher as well, right? Make sense? So here you go. Example. Strings of a guitar. Okay? Strings of a guitar. How the frequency of a string of the guitar, of the string of the guitar, what happens to, not how, what happens, right? What happens to the frequency of the string of your guitar whenever you stretch it further, right? Assume the wavelength does not change when you apply more tension to the string. Solution, right? Here you go. And now you can use that equation, the genetic equation, right? Lambda f, to find out what's going to be the frequency. So that's going to be, let's see, wavelengths before stretching, frequency before stretching, right? And then I'm even going to put here before stretching, right? Tension before stretching. This one doesn't change. Just by stretching the string, you're not going to change the linear mass density. It's linear mass density. Assume that the wavelengths and the linear mass density of the string do not change. Okay? If it changes, very small change. And then after, right? After, like that. Don't forget lambda b is equal to lambda a, right? What you have to do is divide one by the other. You know, let's see, get this one here. Before and after. We're gonna have the same thing here. Okay. Before and after. The wavelength doesn't change. So we can cancel this one with this one. The linear mass density didn't change. Okay, so what's gonna happen? You know, the tension after is more than the tension before. I gotta put the tension before here. Here you go. So this term is gonna be greater than 1. Consequently, the frequency after is gonna be more than the frequency before. Okay. Let's save that. And now we can take attendance and take our break. Roster. Any questions about that? That's another one. Roster. Today is the lecture, the 4th of December. 7 plus that. Yeah, 4th of December. Sky, are you there? Thank you. Gael, are you there? Gael Garcia? Hello, Gael. Okay, it's not answering. Oops, wrong one. Next, read one. Hello, read one. Okay, thank you. Ashley Izumo. I don't see Ashley there. Norberto Lopez.
Oh, I'm here.
Thank you. Vanessa Mena.
Here.
Thank you, Vanessa. Catherine Pacheco. Thank you. Camden Park. What happened to Camden? He was here. Okay, so I'm going to put 0 for now. Marco Sanchez. Okay, and we have 6. Should be 7, right? Because of Gael. Gael Garcia, are you there? Okay, let me give attendance to Camden. He was the first one to arrive. He's always the first one to arrive. So here you go. But then, okay. Okay, so 10:02 right now. Thank you, Vanessa. Break from 10:03 to 10:18 a.m. Okay. I see you in 15 minutes. I'm back here. Okay, so let me just finish with something here. Remember that I told you that before we move to the next chapter, right? So remember, forward propagating wave. Forward propagating wave, right? Remember that? X minus VT. Backward propagating wave. F of X plus VT, right? And what exactly do I mean about that, right? Okay, you already know that. Oh, let's share the screen. There you go. Forward propagating wave and backward propagating wave. That's the most generic expression you're going to see out there. Okay, but then if it's a planar wave, let me copy from before here. If it's a planar wave, it's going to be something like that. Either something like that or something like that, right? But then you can also have other types of waves. It doesn't have to be a planar wave. Doesn't even have to be You know what? I prefer, I don't like that kx. Remember I told you I don't like this kx minus omega t type of expression? Yeah, better. Makes me feel better when I put something like that. The k on the outside, right? X minus vt on the inside. But then you can have other types of waves that are not necessarily planar waves, okay? So you can have a linear wave, forward propagating linear wave, okay? And then a backward propagating linear wave. Notice that in this case, I don't need to put the k because y must be in meters, right? So if the left side is already in meters, I don't need to put another term in there. Now you can see the screen, right, Gael? Let's see, now that Gael is here, I'm going to give attendance to him. Here you go, Gael. Here you go, attendance for you. That's one linear wave. And then you can also have a parabolic wave as well, right? Forward propagating parabolic wave. Okay, here I need to have, it doesn't have to be necessarily k, it can be some other parameter, right? Here I need to have this guy because we have meter square for this term, right? If you have meter square for this term here, I must have a parameter here that is going to be 1 divided by meter. So you have the proper dimension there. The one above was the forward propagating parabolic wave. The other one that below is the backward propagating parabolic wave. Okay, it is possible, but let's not forget, those two are the most important ones. Those two are the ones that you must concentrate. And then you can have all sorts of possible waves, or even exponential waves. You can have an exponential wave as well. Have you thought about that? Here you go, I put up amplitude here, an exponent wave. Okay, and then I go ahead. Remember that I told you the argument of the function must be dimensionless, right? So in the case of my exponential wave, I must have the k there upstairs to make the whole argument dimensionless. That's the forward propagating. And this one here is going to be the backward propagating, and so on, okay? Different types of forward, okay? Different types of forward and backward propagating waves. Among them, the planar wave is the most important one. And I'm going to emphasize that by putting them in boldface. Oh, I forgot to put the positive here, right? Positive and positive. Negative, negative. Okay, good. That's what I want to share with you. And then the next chapter is what happens when waves collide. That's what the next chapter is all about. What happens when waves collide? Okay. The principle of linear superposition of waves. That's chapter 17. Here. Okay, good. You got it. Here in your book, we have an example of superposition of waves. Okay, you have those waves propagating in water. Okay, so here you go. One of those waves right in here producing those wave fronts. We call that wave fronts. But nearby this wave, there's another one that starts right in here, and the front of this wave is interfering with the front of this other wave, forming this interesting patterns that you see out there. Okay, so at a given point, one wave interferes with the other. This is what you see right in here. Is a two-dimensional type of wave. It's more difficult to study. So instead of talking about two-dimensional waves, let's see what happens to one-dimensional wave whenever they superimpose each other, okay? It is possible to have a wave propagating in the forward direction and another wave propagating in the backward direction in the same medium, in the same string, for instance. And that's what you have right now. See here? You have this backward propagating wave and this forward propagating wave. They're going to collide with each other. When they collide, what's going to happen? They're going to combine with one another, just like you see right here. And then they're going to move away from each other. It's possible to model that mathematically, okay? All you have to do, is to sum their mathematical wave forms. That's what you have to do. Here you go, another one, another example. A forward propagating wave is a backward propagating wave, but now in this case, this amplitude is negative and this other amplitude here is positive. The amplitudes have the same magnitude. And then what's going to happen? At a given point in time, they're going to cancel each other. Okay, but because they're still propagating, they don't stand still. Eventually, you're going to see them, in their full format just before the collision. That's what you have to. Here's another type of wave. Okay, this type of wave here is a linear, has a section of a linear wave, right? And another section of the linear wave and another section of constant. A square wave, I'll call it a square, is a section of a triangular wave, a section of a square wave, and a section of another triangular wave. Here we have the same thing. A section of a triangular wave, a square wave, and triangular wave. And they're going to collide with each other. What's going to happen? Whenever they start to collide with each other, this amplitude here is going to be canceled out by this other amplitude here, and so on. Okay? Each pulse has a constant speed, 1 centimeter per second. When t equals to 2 seconds, what's the height of the resultant pulse? Okay, at x equal to 3 centimeters and bx equal to 4 centimeters. Okay, try to figure out on your own how it is gonna be. It's a very interesting problem. It's not difficult. Okay, you can advance it. You see, they have the same speed, right? This have the same speed, 1 centimeter per second. Here is t equal to 0. You know, at t equal to 2 seconds, this wave here is going to advance 2 centimeters, right? 2 centimeters. And this other wave here is also going to advance 2 centimeters. And they're going to cancel out each other because this wave has a larger downward amplitude. I suspect that the resulting wave is going to be downward as well, okay? But try to do that on your own just by drawing, just by making drawings, or you can also use those equations that I showed to you, okay? This one is going to have a section that's going to be like x plus vt, right? This section is going to be x plus vt. This one also is going to have a section that x plus vt. Okay, but just see the and so on. Okay, this one here also you can you can come up with an equation and then figuring out how to and you do the same for this other part. Okay, so let's go back to my notes. Okay, when waves collide, principle of linear superposition. Okay, whenever two waves collide, whenever two waves collide, comma, their amplitude either subtract from each other or either subtract or sum. Subtract from or sum with each other. Okay? Mathematically speaking, it's going to be like that. Let's see. Here is one backward propagating wave. Here is another forward propagating wave. Right? They have the same functional dependence. We go. Same functional dependence. I'm going to call that y1. And this one here is going to be y2. The resulting wave will be, y equal to y1 plus y2. Okay? Y1 is this one here. Y2 is this one here. That's how mathematically it works. Those are exactly the same functions, right? And we can do that for two planar waves, one propagating in the forward direction, the other propagating in the backward direction. What about two planar waves? What about two planar waves, right? What about two planar waves? Okay, let's gonna get it here. This one here. Two planar waves of same amplitude. I'm gonna make things simpler here for you. Same amplitude. We have this one here. And we have this other one here. That's what we call the principle of linear superposition. It's just this a regular linear summation. Just a regular linear summation. Here you go. Copy and paste here. Gonna look like that. And this one right in here. Can be a little bit more picky, right? And put the A in evidence right here. And remove this A right in there. We can do more than that. We can do more than that because there are some sine cosine relations that we can put this guy here in a different format, okay? Because there is some sine cosine relations that we can use right in here. Let's do that. So here you go. Going back to your trig classes in trigonometry. Okay, here what we have, kx minus kvt, right? Kx plus kvt. Okay, like that. And then what you end up getting, let's see, sine k. Let me get that sine of kx, right? Cosine of kvt, of minus kvt, right? And then you have the inverse plus cosine of kx sine of minus kvt, and then you repeat for this other one. Repeat for this other one. We're running out of space here. Let's see if I can put that. Why am I doing that? I'm doing that because it's difficult to visualize what you see right in here. However, if I go ahead and expand those relations, it becomes easier to visualize what we end up having, okay? Like that. And I'm going to put in a different, here you go, y, like that. This term is this one right here. And this term is this one right here. I emphasize that we have a plus sign here. Okay. We can go another step. This negative disappear and nothing else happens to my cosine. This negative, if this negative disappear, then we have to change the sign here because sine of minus a is going to be minus sine of a, right? Cosine of minus a is going to be plus cosine of a. I don't need this positive sign here. I don't need this positive sign here. And let's see if we can do anything else. Do you see this term here? And this other term right here? They're exactly the same with the difference of the signs, right? They cancel each other. So when we combine those two terms, they disappear. Right? And this term here is exactly the same as this one. And we end up with a simpler expression that's easier to interpret. And I'm going to put it in an even slightly different configuration here. I'm going to put the temporal the term that is dependent on the time, right? The temporal dependent term in front of the term that in front of the spatial dependent term. The spatial dependent term, temporal dependent term. I'm going to write down in a slightly different way as well. And now I'm going to call this term here. Okay, let me see how I'm going to call it a function of t. Okay. And now it starts to become easier how to visualize what you have here. Okay, this is my term that's dependent on time. This is my term that's dependent on time. Okay, and how does it look like? Okay, it looks like the following. You know, you have a sine function, right, in space, and this amplitude is changing as time goes by between -1 and -2. -1 and +1, right? This cosine kVt, you know, change from -1 to +1. And the total overall amplitude becomes anywhere between -2a to +2a. So what we are going to have, we are going to have a sine wave that's going to oscillate back and forth. And I have a simulation for you here, so you can visualize it better. Okay, let's see, is that the one? No, that's not. Is this one right in here? No, not the one I want. I want this one here. Okay, here you go. Okay, so what did I do here? I did exactly what you see there in my equation. I have the temporal dependent term and the spatial dependent term. Okay, right here. And let's put this guy to move. Let's see here. I have my wavelength is 100 meters. I have the speed. Let's zoom in so you can see better. I have this speed here of 25 meters. And the instant, this one is going to be, let's see here. Yeah, I do not know what the 6 is. But here is time. I'm going to put a time instant equal to 0. Okay? At time t equal to 0, you have maximum amplitude for this wave. A little bit later, the amplitude goes down. The amplitude goes down. The amplitude goes down. The amplitude goes down, right? Until you have what we call destructive interference. This is called destructive interference. Okay, and then as we advance, we're going to start to get more and more constructive interference. 1.6, right? 1.6, 1.8, 2, right? Can we go further than that? Let's see what's going to happen. 2.2. Okay, now it's going to revert direction, right? Here is the point of the instant of time of maximum negative amplitude. And now go back 2.2. That is that cosine of omega t term that's modulating the amplitude of the wave. We call that modulation of the amplitude. Okay, 3, 3.2, 3.4, 3.6. Let's see. 3.8. It looks like we're reaching the point of maximum amplitude. So between 0 and 3.8, we have a full period of the wave. Okay, let's see 4. Oh, no, it's between 0 and 4 is the full period of the wave. Okay, let's see 4.2. Yeah, now it's going back. Between 0 and 4 is the full period of the wave. Since we have lambda is equal to lambda over period, right? Equal to V, right? Do the math here, right? V is lambda over T, right? Which, so for T, we get lambda divided by V. Lambda is 100, V is 25, then we get a period of 4 seconds. Okay? So that's what we get for this specific case of interference pattern. Two waves, one propagating, both waves having the same amplitude, one propagating in the forward direction, the other propagating the backward direction. This type of wave has a special name, and it's the type of wave that we see in the string of a guitar. Okay? That's a standing wave. That's a standing wave. And that's the model, mathematical model of the wave in the string of a guitar. When you pluck the string of the guitar, we see this vibration, right? With a single lobe. Okay? And now let's see. Go back in time. Go back in time until we go to t equal to 0. And then I'll play the movie for you, right? I made a little mistake along the way. Okay, here you go. Start right here. You go. Oscillate back and forth. Oh, what happened here? Yeah, it looks like it went. Let's do that again. Let's do that again. 0, 0.2, 0.4, 0.6, 0.8, 1, 1.2, 1.4, 1.6, 1.8, 2, 2.2, 2.4, 2.6, 2.8, 3, 3.2, 3.4, 3.6, 3.8, 4. Okay? And now let's go back in time until I reach t instant of time t goes, and then we can go forward again. Here you go. That's how it looks like. Okay. Just one oscillation that I did that for you. That's okay. What you have right in here, and I'm gonna put here. What you have here is a standing wave. Standing wave. It is standing because it appears, so don't forget, it appears the wave is not moving. The resulting wave, right? The wave is not moving. When in reality, you have two waves moving. One along the forward direction and the other along the backward direction. Yeah, like that. So there is one more type of problem that you have to know. Another type of wave, of wave phenomenon, right? Is beats. Okay, phenomenon. A phenomenon, let's see. Is beats. I'm going to give an example of beats. Okay, beats is a very interesting. Beats is a very interesting phenomenon, which can be reproduced right here in the classroom using software available in the internet. Okay. Okay, by definition, bits is the interference of two waves having different frequencies. Okay? Interference of two waves of same amplitude, okay? Don't forget, same amplitude. You don't want to complicate that. If you're gonna do different amplitude, the problem becomes far more complicated mathematically. Okay. We can see this type of effect for sound waves. And that's where we have to go back to 16.5. Okay, here you go. Well, I'm going to cover 16.5 quickly so you can. Okay. Okay. Like insert page break so I don't get one. Okay, so here you go. We cover 1, 2, 3, and 4, but there is one more thing that we have to cover here. 16.5, okay, which is sound waves. So you can understand better that it goes 16.5, nature of sound, okay? Nature of sound. The nature of sound. No. Sound, already mentioned to you, sound is a longitudinal wave. And what do I mean by longitudinal wave? I'm going to give an example here. You already saw it, a transverse wave, right? Let's see here. Moving, so let's see this one here. No, not this one. Okay, here you go. Here's an example of a longitudinal wave. Sound can be modeled as being a wave that propagates in air. And when the wave propagates in air, what's going to happen is going to compress the air and distend the air. That's a very good model for this, for the sound, producing pressure difference. That's what you have to know about sound, okay? Sound is a longitudinal wave that can be modeled in terms of pressure waves that propagate in air. As the wave propagates in air, it compresses the air and rarefies it. Can you picture that? So going back here, I'm gonna play the movie, right? So let's see, that's t equal to 0. At a given instant of time, t equal to 0, you know, you have regions of compression of air and rarefactions, air rarefactions as well. Okay. As time goes by, what's going to be? You know, you're going to see this wave propagate from the left to the right. Okay. Oh, I'm sorry. This one is not a wave propagate from the left. So this is a standing wave. Let's see if I have another one. Oh, here you go. That's the one I want. Must be this one. Let's see. Okay, so here you go. 0.2, 0.4, yeah, 0.6. See that? The wave propagating from the left to the right. The compressions, right? Propagating from the left to the right. 1, 1.2, 1.4, 1.6, right? 1.8. And that's exactly what happens when we hear each other. We don't see that at the microscopic scale, but that's exactly what happens. We have more higher and lower pressures we see in this column of air. Higher and lower regions of pressure in this column of air. 2.2, 2.4, 2.6. Here what I did, I made one of the air molecules very large, so you can see that it's just oscillating back and forth. 2.8, 3, 3.2, 3.4, 3.6, right? 3.8. Let's go to 4, and then we can go back in time. And we play the movie. Okay, here you go. Now I'm going to undo it, to redo it. You go the wave propagating to the left, propagating to the left, propagating to the left, right? To the left, no, to the right. To the right. And this air molecule is just oscillating back and forth here. Here you go. Redo it. See the compressions propagating to the right, but the molecule, the large molecule that you see in there, is just oscillating back and forth. And now going back in time, these compressions are going to move to the left, right? Because I'm going back in time, playing my movie backwards until we reach 0. It's kind of an illusion what we see, kind of gives you the impression that something is moving. Okay, so going back to my right here, no, this one here. So that's the model of air that you have to have in mind, okay? That's the model for the air molecules when sound, that's the model for the sound when it propagates in the air. Okay. Now, there's something else that you have to know about sound. Different frequencies of sound have exactly the same speed. Okay. That's what you have to know about sound as well. And it is around 330 meters per second. It's very fast. Okay, 330 meters per second in air. Okay. Depending on the temperature of the air, it changes a little bit. It changes a little bit. Well, we also call that Mach. This speed is called Mach 1. 1 times the speed of the sound. And Mach 2 is twice the speed of sound. Mach 3, 3 times of the speed of the sound, and so on. Okay. So because of this constant of the speed of the sound, right? V, different frequencies is going to have the same speed. But in order for different frequencies to have the same speed, the wavelength of the sound must change, okay? So here you go. It's gonna be something like that, you know, a wavelength 1 times frequency 1 must be equal to a wavelength of 2 times the frequency 2. Okay, that's an important characteristic of sound, which is, you know, 330 meters per second.
Professor, I have a question.
Yeah.
Why did you color the 16 and 17?
Let's see. Are you talking about 16 is the chapter in the book?
Okay, so
In the books, okay.
that's
Okay,
going to be on the test, right?
Yeah, 16.5 is going to be in the test. Yes. Previously, I told you that we were going to cover only up to 16.4, but we are covering 16.5 as well. Okay.
Okay.
Okay. So that we need this information here to understand what comes next in chapter 17. And let's see. Principal linear superposition 17.1, constructive and destructive interferences 17.2. And now we are covering, we're going to cover 16 point. Let me put just here the names, so you know what that the principle of linear superposition. Okay. Here, constructive and destructive interference. Right. We're going to skip 17.3 beats. 13.4 is beats. Okay, 17.5 is transverse standing waves, and 17.6 longitudinal standing waves. Okay, so 16.1 is nature of waves. The nature of waves. 16.2 periodic waves. 16.3 the speed of wave, the speed of a wave on a string. This one is the mathematical. I like to do the mathematical description of wave. It's not that difficult, okay? Of a wave. And then, you know, the nature of sound. The nature of sound. Okay. Chapter 16. Chapter 16, waves. Chapter 17, waves and sound. And sound. Principle of linear superposition. Principle of linear superposition. And interference. Okay, like that. I'm gonna put that in. Yeah, leave it in red color, right? Leave it in red color. We have to do that so you can do beats. You have to cover sound so you can do beats, okay? Let's see if I can find. And now different frequencies of sound have exactly the same speed, okay? So going back to beats now. Beats is the interference of two waves of same amplitude having different frequencies, okay? There you go. That's what beats is all about. So get two sound waves of different frequencies. Okay, the result, the different frequencies in air. Okay, the result will be two sound waves of different wavelengths as well. Okay? Then interfere them and see what happens. See what happens. Okay? So the way it goes mathematically, it goes like that. It's very similar to what we did right in here. The only difference, all right, here you go. Here's gonna be K1, right? V remains the same. Here's gonna be K2. V is gonna be the same. And now I am going to 2 pi over lambda 1, 2 pi over lambda 2. Why? For lambda 2. Let's see. Oh, and by the way, they're propagating the same direction. Get two sound waves of different frequency in the air. Here you go. By definition, this is the interference of two frequencies in the air and propagating along the same direction. Okay. So what was positive here must be negative, one dimensional. Okay, and let me get, how do we reproduce something like that? Okay. Let's see if I can. I have a drawing here for you. No, I had to do it from scratch. Okay, it's gonna be like that. Okay, so it's gonna be here you go, one speaker and another speaker. One at a frequency, at one frequency, F1, and then another one at a different frequency. Okay, and somewhere, and you have placed yourself somewhere around here along this axis. Okay, you have your ear here or your microphone, either your ear or your microphone. You're detecting what are you going to hear. Okay, the angle here is very small. Okay, so you can consider that being a one-dimensional phenomenon. Before we move forward with this, let me make a demonstration. Okay, let's see. Let's go to the internet here. Harmonic. Harmonic simulator, right? Harmonic simulation. Sound harmonic simulation. 11:10 already. Time for our making for sound harmonic. Let's take our break. Okay, and then I'll get that out. That's the one. Let's see. Let's see if that's the one. Sorry to bother you. Mandatory cookie drill. Let's see here. No, that's too much. That's too much. Sine waveform simulate. Maybe this one here. No, not this one. Receive wave interface harmonic vibration acoustic simulation. Is that the one? No. Gosh. Sound waveform simulation. Give me another 3 minutes if I don't find it in 3 minutes. See here, simulation questions. Oh gosh, sound waveform simulation, waveforms. Sound waveform, it will be here. No. Go back here. Live movement. Let me see tutorial. Standing sound wave. How come okay, let's have our break. Okay, and then when we come back from the break, I'll find this sound simulator. The best way of understanding beats is to go through this harmonic simulator. You're going to see what an interesting effect it is. Okay, so here you go. Mathematically, that's how we treat it. I'm going to elaborate on that once we come back. Okay, and break from 11:13 to a.m. to 11:28 a.m. Okay, so I see you in 15 minutes. I'm back here and I found the site that I was looking for. Okay, what's going on here? Okay, here you go. That's the one. I'm gonna share that with you, and then you do exactly what I do too. Okay, in your in your spare time, so you can play a little bit with this online tone generator. Okay, I'm gonna put that in my notes as well. Online tone generator. You might want to practice it there in your computer while we do that. I'm going to send, here you go, online tone generator. I use this online tone generator every time that I teach waves. Here you go. Okay, so here you go. This online tone generator is especially useful if you want to understand beats, this phenomenon of beats. I have here a wave, a sound wave of 440 hertz, okay? And I can change the wavelength of this wave. That's the volume, okay, volume. And I can change the wavelengths, the frequency of this sound. Yeah, I can play it. See, that's what 440 hertz sound like. Stop. And I'm gonna put, the human ear can hear from 20 hertz to 2000 to 20,000 hertz. Below 20 hertz, we call it infrasound. Above 20,000 hertz, we call ultrasound, okay? I'm gonna put that here for you as well. Okay, and it goes, the human ear can detect sound between 20 hertz and 20,000 hertz. If sound frequencies below 20 hertz are called infrasound, whereas sound frequencies above 20 kilohertz, right? 20,000 hertz are called ultrasound. Okay. And then we're gonna get here 20 hertz. Let's see if you can hear anything. 20 hertz. I don't hear anything. You know, even though you're supposed to hear at 20 hertz, let me increase the volume. When I increase the volume, I'm increasing the amplitude of the sound. I don't hear anything, folks. Do you hear anything? I don't hear any. Let's see, 30 hertz. But in, you know, theoretically speaking, we're supposed to hear something like that. I don't hear 30 hertz either, and I'm using the highest possible volume, 40 hertz. 40 hertz. Maybe it's because of my speaker that doesn't pick up, that doesn't reproduce sounds at this low frequency, okay? Let's see, 50 hertz. No, I don't hear anything. What about 100 hertz? Ah, I hear. 100 hertz I hear. It's the bass, right? If I go to 75, let's see if I can hear anything on 75 hertz. Barely. Barely. I hear 75 hertz, barely, okay? And we are playing with this guy. Let's see, 20,000 hertz. 1, 2, 3. Maybe my hearing is not good at this frequency either. Yeah, I don't hear anything. 20,000 hertz. Let's see, 10,000 hertz. Yeah, I hear something. I hear. What about 15,000 hertz? Remember, sometimes it's not because of my ear or your ear, okay? Maybe it's because of the speaker in your computer that doesn't produce well those different frequencies. Let's say 15,000 hertz. I don't hear anything at 15,000 hertz, and I'm on the highest possible volume. Nope, I don't hear anything. But anyway, let's go back to 440 hertz, right? That's what I'm gonna bring down the volume, okay? Stop, right? In order to reproduce the beating phenomenon, what you have to do? You have to have two sound waves. It's not just two sound waves, can be any other type of wave. Okay, it can be a wave in a string, okay? It can be even an electromagnetic wave. You have to reproduce two waves of slightly different frequency. Slightly different. Here is 440. Here is 441. Okay? And you have to interfere, you have to play them simultaneously, and you're going to see an interesting effect that happens. Okay, here you go, 441. 440. It's slightly different, right? And now what I'm gonna do, I'm going to interfere those two sound waves. How do I do that? I copy this address, right? This address of the site, and open in a different window, right? We're going back to the same place, okay? Here you go. Here's one window in my browser, another window in my browser. Okay, the only difference that they have is exactly the same frequency. I'm going to change those two frequencies, and I'm going to overlap the sound that they make, that they produce. I'm going to interfere the sound of those two windows simultaneously at the same volume. Oh, it's slightly different volume. I wanna keep them the same volume. Let's see. See that I have those options, okay? I can have the sine wave, I can have the square wave, a triangular wave, I can have a sawtooth. The one that we should be working on is the sine wave. Okay, so let's play this 440 hertz wave, okay? And I'm gonna play the 441 hertz wave. Do you hear what's happening? We have this sound that comes loud and goes away, come loud and goes away. That's what we call beating. It is as though it's keep on oscillating, right? This type of phenomenon is beating. That something like that happens whenever you combine waves of different frequencies. Okay? If I stop this one, you're going to hear just the other one. If I stop, see that? I'm gonna play this one again. Okay? if I change slightly this frequency, 442 hertz. Now we have 2 hertz of difference between one and the other. Look what happens to the beating. See that? A little bit faster. The higher the difference between the frequency, the beating becomes a little bit faster. Okay? 443, right? See that? This frequency that you see, you know, is 3 hertz. This peak that you hear has a frequency of 3 hertz. 443 minus 440. The higher the difference, the more difficult becomes for us to perceive the beating phenomenon. Okay, right now it's 4 hertz difference. Right? This type of phenomenon can be modeled mathematically, so you can understand what happened. Here you go, 445, now 5 hertz difference. 5 hertz difference we still can perceive with our senses. Things start to become complicated above 5 hertz. Let's take a look at 6 hertz difference. Oh, we still can perceive, right? We still can perceive. But what about 450? 10 hertz. 10 hertz of difference between this one and this other one. Okay? Becomes faster and faster, right? And now I'm gonna put 60 hertz difference. 60 hertz difference is gonna be 500 minus 440. Okay? Now we cannot perceive the beating frequency because the frequency is so fast that we can hardly perceive the beating that happens in there. It's a, remember, 60 hertz difference. Up to 10 hertz, we still could hear that. We still could perceive it. Let's take a look at 440. Let's put a 460, right? 460. Here you go. Hardly, right? Okay, I'm going to stop it. Okay, and we can go the other way too. Let's see, I'm going to stop the other one as well. Here you go. Let's see if this one can, you know, some of those, let me try 440.1. Oh, yeah, we can do that, 440.1. Now I'm going to come up with a difference of oh, this one is 460, 440, here you go. We're going to come up with a difference in frequency of 0.1 hertz only. And look what happens. Now, the 0.1 hertz is too much. Let's do 0.5. Half hertz. Okay? Play it. Do you see how slower the beat is? This time period that you hear between the louder, each consecutive louder is around 2 seconds or half hertz. Half hertz is a period of 2 seconds, right? Going back to our frequency of 441, in which you have just 1 hertz of difference, that corresponds to a period of 1 second. Okay? What you hear right now corresponds to a period of 1 second. And if I put 440.1, then there will be a period of 10 seconds. See? Now we can perceive better, right? This period that you're experiencing right now in the beats correspond to 10 seconds. You can even time with your watch. You can even time with your own watch. Okay? Go away and then start building up again. At the peak, intensity represents the difference in time between peak and peak to peak is going to be 10 seconds because we have 1/10 of a hertz. 1/10 of a hertz corresponds to 10 seconds of period. Okay? And like I said, this phenomenon can be exploited mathematically. And that's what we are going to do right now. 1144. Okay, it's a little bit lengthy, the derivation, but it's going to be worth it. Okay, and I am going to do the following. I'm going to, I stopped writing here, right? One frequency, another frequency. One wavelength, another wavelength, right? Because we are talking about sound waves, the speed of each different wave are exactly the same. Let me copy and paste it here. Okay, so here you go. V equal to, don't forget, lambda 1 times F1, right? But V is also equal to lambda 2 times F2. Lambda 2 times F2. I will write lambda 1 and lambda 2 in terms of their frequencies. I will write, yeah, that's right. And then what do we get? Lambda 1 becomes V divided by F1, right? And lambda 2 becomes V divided by F2. Okay. And then just to, to put my equations in terms of the speed and the frequency, I'm doing that so I can replace, lambda 1 and lambda 2 in terms of the frequency and the speed, okay? So lambda 1 goes here. Lambda 2 goes here. Okay, here you go. And I'm gonna go the next step. F1 goes upstairs. V remains downstairs. F2 goes upstairs. V remains downstairs. Okay, like that. Now it's in the format that I want. Okay, same amplitude. I'm using here same amplitude for those two waves. Okay, so we're running out of time. I'm not going to do the full derivation. All I'm going to tell you is, let's see, 1148. Well, what you have to do here? Okay, you have to do here is the following: expand the thing, and applying some trigonometric relations. That's what you have to do. Okay, and when you do that, let me see if you get here the beats. Right here. Let's see if you. Yeah, unfortunately, your book doesn't give you the total result, unfortunately. But here you go. But here, that was exactly what we experienced, right? The sound becomes higher right in here at the spot, then it decreases. When you sum those two waves, right? It's slightly different frequency. You're going to get a plot like that. Okay, this frequency that you see here is a frequency F1 minus F2. Okay. And it becomes louder and fainter with that frequency that you said, F2 minus F1. Okay. Let's see if I can get. Okay. When you apply the proper relationships, you get something like the following. You get, let's see. You're going to have a term that is going to have a high frequency. Okay, something like that. And another term that's going to have a lower frequency, but it's going to be a multiplicative factor, something like that. There might be a mistake, a little mistake in there in terms of the signs, but it's something like that. Okay. Oh, yeah, and it shouldn't be 2 here, it should be 2 here. Okay. Note, see, this is the term of high frequency. That's very difficult to pick up by the human ear. 440 plus 441. And here's the term of low frequency that's easier to be picked up by the human ear, 1 hertz, for instance. So that period of high and low frequencies, right? That period that you heard in which the amplitude goes high correspond exactly to this term here. And I'm gonna put it right here, okay? I didn't do the full derivation, but if you do, you're gonna get something like that. What is a summation? Becomes a multiplication, but becomes a multiplication in terms of the difference between frequencies and the sum between the two frequencies. When you plot something like that in a graph, just like you saw, you find this plot here of the wave going up, the distance from here to here is related to the beat frequency, F2 minus F1, that correspond to a longer period, okay? And a full oscillation here represents F2 plus F1, divided by 2, by the way, okay? F2 plus F1, that is more difficult to pick up by the human ear, okay? That's what a beat phenomenon is all about, the beat effect is all about. Do you have any questions? We have 8 more minutes to go. Yeah, it's unfortunate that this book doesn't do the full derivation, but doesn't even have the final formula, but it's what you saw in there. Right? Let's take a look here. Beats. In physics. Beat, okay, Wikipedia. Okay, here you go. Even better. Okay, see, he put that like a cosine and sine. Okay, here is the beating frequency, is the F2. Let me see. Okay, that's the one. Okay. What you saw in your book is like something like that. What the book didn't show is the envelope around it. With the envelope, we can see that this envelope has a frequency, a longer frequency than the inner frequency of right in here. So the beat frequency is this one right in here. F2 minus F1. He didn't put F2 minus F1, but that's what it is. And this one is F2 plus F1. Okay. Here's the superposition of the waves. Okay, the blue is the resulting interference. The brown and the green is each one separately. Okay, here's the actual equation. 2 pi, there's no V in there. Yeah, there's no V because he didn't do that for sound waves. That's why there's no V in there. Okay. And let me see. And we gotta make sure. Wait a minute. We gotta make sure that this thing. Okay. That's because, yeah. Okay. We must have my V here because we have meters here, okay? He didn't do for sound waves. That's why it looks like a slightly different. Okay, but this equation is not incorrect. The only thing that might be wrong is going to be this term here. There should be cosine. Okay, we have 2 pi there. Let's see. Yeah, we should have 2 pi here upstairs as well. We should have 2 pi here as well. Okay, and I'm going to write down just like that, divided by V. Take out this V out of here. Notice that he didn't put x minus vt, right? What is he doing? He's doing this thing for a specific instant of time. And then I'm going to put this one right in here as well. Okay. And now we have a better expression. Okay. So when you select a specific place in space, say x equal to x1, right? Like just we were listening to that sound, we were not moving the head, right? The head was just in the same place, the same x position of my ears, right? X1, and I'm gonna do even better. I'm gonna make it equal to 0. Okay, the above equation becomes simpler, right? Okay, so here you go. Eliminate this guy here, right? This V cancel out this V, and we get the same equation that is there in the book. The negative of cosine of the argument of the cosine is the cosine. Okay, the V goes away. I want to put a negative in front of this V disappear, becomes just T. And now it's very similar to what we have there in Wikipedia. It's doing that in terms of cosine. That's why it's slightly different, okay? But the important feature is that this term here and this other term here, that's the important feature. When you sum 2 waves of 2 different frequencies, okay? When you sum 2 waves of different frequencies, you get the behavior of a wave having an amplitude that is modulated by the difference of the frequencies and you get the behavior of a wave having two circular terms, right? Circular function terms, one having an amplitude that's one having a variation, right? A temporal variation in terms of the difference in frequency, and the other a temporal variation in terms of the sum of the frequencies. Like that. Okay, 11:59 right now. And I hope I can cover a little bit more next Wednesday. As at this point, I haven't covered those 2 yet, okay? So we cover, those 2 shouldn't be difficult to cover. I cover all those 5. And hopefully we'll be able to finish those 2 next time. If you don't, then, All you have to do is to worry about those 3 sections, okay? Any questions? So, yeah.
I have some questions after the class.
Okay, good. Okay, so you can stop down, and I see you. If you don't stay around, I see you on Wednesday.